Okay, here we go. Hold on to your hats. Module 7, it's Chapter 10, Hypothesis Testing. Hypothesis testing of a sample mean or a proportion. I've got some data. I generated some fake data again, and let's see, what do I got? I got customer ratings. Well, that sounds familiar, doesn't it? Rating scale goes from 1, which is good, to 5, which is bad. And what are we rating? Well, I thought it was appropriate for the time of year. We're rating a mall Santa. Okay, so I got customers. Customer 1 down to, oh, got a lot of customers. I got 50 of them, and they all gave the mall Santa a rating. Okay, now the first thing we're asked to do is generate some sample statistics. Again, it's the mean, the standard deviation, and the confidence interval. Again, this was last week's work. How do we get the mean? Well, in Excel, it's so simple. We can use the average function. Standard deviation, there's a stdev function, which gets us the standard deviation. I use the count function to count up my number of samples, and we know degrees of freedom are 1 minus n, 49. Okay, in this case, we need a critical value. Remember, we're going to have a critical value that we are going to compare our test statistic, our calculated test statistic with. So, in this case, we were told, oops, I think I made a mistake there. No, that's correct. We were told to use the 0.1 alpha level. That's right. Here it is, right there. And so when you look up a t critical, since we're looking at a two-tailed distribution, we have to have half of that, or 0.05. Again, it's that our h naught is something's equal to something versus it's not equal to something. That's a two-tailed distribution. That's different than if we're saying something is less than something and the alternative is something is greater than or equal to. Boy, that sounded confusing. No matter. Move on. So I looked up critical value in the back of our text, and I found 1.667. And here's something I haven't shown you. Excel also has a pretty nifty function. It's called the TINV, T inverse function. And let's see, what it'll do is it'll give you a t-value. You need the probability level. And for us, you got to know that you don't put the 0.05, you put the 0.1 in this case. 0.1, and it wants degrees of freedom. And degrees of freedom in our case is 49, and lo and behold, look at there. The same value, 1.677. Isn't it? Sure looks like it. Get rid of some of those decimals. Same value. Okay. Delete him. Don't really need him. I got him written down right here. This is, again, our critical value. We're going to calculate our t-value and compare it to this eventually. We're not there yet. We're just doing the basics. Okay, let's see. Confidence intervals. We know how to do those. What's the equation? Well, that's in Chapter 9. We take, let's see, we take E8, which is the mean, and we subtract from it the test statistic in E12 times E9, which is the standard deviation, and divide by the square root of n. And you've done that already. So the lower confidence level is the mean minus that. And the upper one is the mean plus that. And when you do that, I got these two values, and I just rewrote them as a confidence interval here. I am 90% certain that the true mean falls between 2.77 and 3.43. Again, this is last week's work, but we're going to repeat it today. We calculated a sample mean of 310, but we believe that the confidence interval, 90% confident that the true mean of the population falls between 2.77 and 3.43. Okay, I did some little frequency distribution work here just to see what my numbers look like. I actually generated those using a random number generator within Excel. And what did I find? Let's see, ratings of 1, there were 8 of them, 2, 12, 7 3s, 13 4s, and 10 5s. So it looks like, yeah, it makes sense that it's a little bit pushed towards the high side, and our average tells us that, doesn't it? If this was perfectly random and we had millions of samples that we did, we would expect to get 2.5, but our mean is slightly higher, and this distribution data shows it. Okay, let's do our hypothesis test for the mean. How do we do it? It's this center column here. First of all, again, we already said this, the alpha level is 0.1 and alpha over 2 is 0.05, and I needed that when I went in and got my t critical value from the t table. Now, I'm going to look at 3 different cases. The first one, I'm going to have a null hypothesis that the hypothesized mean of the population is 2.5. And of course, the alternative hypothesis is that no, it's not equal to 2.25. And now I need to calculate my test statistic from my data. Here's the equation. This is our chapter 10 equation, and you'll find it throughout the chapter. I'm just looking at the equations section in the back of the chapter, page 356. It's right there in the upper third. Testing a mean, population standard deviation unknown. So what do? We take E8, which is our sample mean. We subtract our hypothesized mean, which is 2.5 in this case, and we divide by E9, which is our standard deviation, divided by the square root of n. Sure enough, that's our equation. And I got a value of 3.02. Now, how did I get this reject H0? I'm saying, no, I calculated t-stat of 3.02, and I'm rejecting H0. I do not believe, I cannot say based on statistics that the mean, the hypothesized, the true population mean is 2.5. I'm rejecting that idea. How did I do that? Well, what we have to do is compare our 3.023 to our critical value. Now keep in mind the t-distribution. At some point, we drew a line up to the curve and said, that's our critical value. It's at 1.6, and because the t-distribution is symmetrical, the other one's at negative 1.67 or 68, 1.68. Now, the value of 3.02 falls well to the right of 1.68. Therefore, we must reject H0. We cannot accept it. We must reject it. And we say, no, based on what we're seeing here, the mean is not 2.5. Again, our sample mean was 3.1. No, they're quite a ways away. Okay, let's do another one. Let's bump it up a little bit. Let's propose that the true mean is 2.75. Of course, the alternative would be that it's not 2.75. What changes in the equation? Not much. One value right there, the 2.75. That was 2.5 in the earlier case. All the other stuff is the same data. And now it says, let's see, I got a value of 1.76. Well, this is still to the right of 1.68. It is still in the reject region of the t-distribution. We can't accept H0. Uh-oh, wait a second, I've got accept there. I think I changed it red, but I didn't change the words. Ooh, sorry about that. Let's copy that and put him down there. Yes, because, oopsie, we are outside of our critical value. We must reject the null hypothesis. We don't think that the mean is the true mean is 2.75, not based on our statistics. Let's do a third one. Well, we're getting close to what our sample mean is. Let's say, let's propose that the mean is, the true mean, the population mean is 3.0. And this time, look what happens. We calculated things the same way. The only thing that changes is right there, the hypothesized mean. Otherwise, we're using all the same values in that equation. And this time, we had a value of 0.5. Well, where does 0.5 fall compared to 1.67? It's inside of 1.68, or more towards the main part of the t-distribution. It's in the accept region. In this case, we accept H0. We say yes. We believe that the true mean of the population is 3.0. And our statistics say with 90% certainty that we should accept that fact. Okay? So what did we do? We looked at three values. Three hypothesized population means: 2.5, 2.75, and 3.0. The 2.5 and 2.75 were both rejected. No, we can't accept that those are the true means. But 3.0, our statistics showed us that, yep, we should accept that. Now, I want to compare these values because they asked you about this in the question. How do these values compare to the confidence intervals that we calculated? Well, look, we were at the 0.1% confidence level. And again, this is my t-critical. The alpha level is 0.1, but this is where I went in the table to get a 0.1, right? Yes. Okay. So we're comparing the same thing with both these cases. In one case, when we made our confidence interval, we said we were 90% certain that the value should fall between 2.77 and 3.43. When we did our hypothesis testing at the same level, 90% level, we said, no, we do not believe that the true value of the population mean is 2.5. We'll compare that 2.5 to our confidence interval. It falls outside of it. It makes sense. Our confidence interval and hypothesis test are telling us the same thing. We do not believe that the true population mean is 2.5. Our t-test told us that, and our confidence interval tells us that. Okay, let's look at a bigger value, 2.75. Well, let's see, 2.75, does that fall in our confidence interval? Not quite. But look how close our calculated test statistic, t, and our t-critical are to each other. They're very close, but we just didn't make it. 2.75 is not inside the confidence interval. Finally, you know where this is going. In the third case, 3.0, does it fit? Is it within the confidence interval? Yes, it absolutely is. And so that is why we accepted that the true population mean is 3.0. And our confidence interval, again, we were 90% confident that the true mean fell within there. Those two jive. T-test, hypothesis testing, and confidence intervals tell us the same thing. Okay, I think I'll take a break here. And my throat's giving me trouble, so I'm going to get a drink of water. I'll be back with part 4, hypothesized testing for proportions.